This is part D for our unit on exploratory factor analysis. Now, up to this point, I have been talking about principal components analysis. And all the examples we have been looking at have been examples of principal components analysis. And we are now ready to go on to talk about factor analysis proper. Now note that sometimes people make a big deal about the difference between principal components analysis and factor analysis. And when people make a big deal about the difference, they note how it's important to be precise in the language and to use the word components whenever you're doing a principal components analysis, and to not call your components factors, and to use the word factors whenever you're doing a factor analysis, and not to call your factors components. So if you want to make a big deal about the difference, then you'd want to pay attention to language and be precise, and make sure you use the word components and not factors when you're doing principal components analysis, and use the word factors only when you're doing an actual factor analysis. Now, as you've noticed, I often slip into using more loose language, and I often end up calling everything factors. Even when I'm doing principal components analysis, sometimes I end up calling my components factors. And this is actually relatively common. And I think one reason why it's common is that the distinction between principal components analysis and factor analysis is actually relatively subtle. It's not that big of a difference between the two. The key difference is simply this. When I do principal components analysis, I do not include anything in my formulas that make an allowance for measurement error. In contrast, when I do factor analysis, I'm going to add something or use an extraction method that makes some kind of an allowance or an assumption that my items have measurement error. That is, if I have a set of items that are indicators of a factor, with factor analysis, I assume that my items do not perfectly indicate the factor, that my items have some degree of measurement error, that is, there's some degree of unreliability, and so I want to take an account for that unreliability, that measurement error, when I calculate results for my factor analysis. With principal components analysis, we simply don't bother to worry about measurement error. And that is really the key difference between principal components analysis, where we extract factors and don't bother to make any kind of allowance for measurement error, and factor analysis, where we assume that our items have some degree of unreliability, that our items are not perfect indicators of our factors, and therefore we need to make some kind of allowance for measurement error when we extract factors. Now, when we get into factor analysis proper, we actually encounter several different ways that we can go about extracting factors. There's a wide range of options that are available to us. I'm going to talk about two specific options that are probably the most common and popular options, but note that these aren't the only options. So probably the one option that's been around the longest and maybe the most widely used option is to do something called principal axis factoring, or principal factors analysis is another term for the same thing. So if I call it principal factors analysis, is the same thing as doing principal axis factoring. And another approach that we can do to extract factors, if we're doing factor analysis proper, is to use an approach called the minimum residual approach. And as I mentioned, there's several other approaches, but in the next few slides, I'm going to show you what principal axis factoring is, and then what minimum residual factoring is. So let's take a look at these. Now, before I proceed to tell you about how we extract factors using factor analysis proper, I need to back up and clarify and review a few things about how we extract factors when we're doing principal components analysis. So if you were all excited about leaving principal components analysis and moving on to something new, hopefully this doesn't disappoint you too much to go back and say a few more things about principal components analysis. So what I want you to do is to go back and recall what happened at that very, very first step that I talked about, where I said I create a new variable called factor score A. Or if I wanted to be precise in my language, probably I should have been calling this component score A, because we were actually doing principal components analysis. But I called it factor score A, and I said we create this thing called factor score A by taking each item on our questionnaire or each item on our assessment instrument, each X variable, and we multiplied each score times a weight, a beta weight. And then we summed these weighted items together to get a score on factor score A. And recall where these weights came from. How do we determine what weights we should use, that we multiply each item by what weight? How do we decide what these weights are? And recall that I said what we do is we want to use matrix algebra and figure out what weights, what system of weights will produce a factor score that will explain as much as possible of the variance in our original X items. And so I talked about we use this matrix algebra procedure to maximize the proportion of variance in all the X variables that is explained by that factor score. And so that is essentially the method we're using to extract factors when I'm doing principal components analysis. I'm using this matrix algebra procedure to calculate a factor score so that that factor score will explain as much as possible of the variance in my individual X items. So let's take just a moment to see exactly what we're doing when I say we're using a matrix algebra procedure to do this. What does that matrix algebra procedure look like? I want to tell you just a few things about that procedure. So this slide gives you a little bit more information about what that matrix algebra procedure is. That procedure that will calculate the loadings when we're doing principal components analysis. That matrix algebra procedure that will calculate loadings so that if we use those loadings to create factor scores, those factor scores will explain as much as possible of the variance in our original items. What does that process look like? So when doing principal components analysis, it basically goes like this. We need to start off with a correlation matrix. And actually, when you're doing a principal components analysis, and this will actually be true as we'll see in a moment with factor analysis as well, that really all you need to start off with is a correlation matrix. And if you were going to do hand calculations, you would start off with a correlation matrix. You wouldn't need to start off with your entire data set. You just calculate a correlation matrix, that is a correlation matrix of the correlations between all the items. So if I had a 6-item questionnaire, it would be a 6x6 correlation matrix. And so I get that correlation matrix showing the correlations between all the items on my assessment instrument. And then I'm going to do a procedure, a matrix algebra procedure that is called, I'm going to diagonalize the matrix. So I take a correlation matrix and I do this procedure, which is called diagonalizing the matrix. And once I have done this procedure where I have diagonalized a matrix, I can use that output to calculate my factor loadings. That is, I can calculate those weights that I use to create my factor scores. And those weights are the same things as the loadings when I look at my component loadings, such as the pattern matrix or the structure matrix. So, and to clarify, when I diagonalize a matrix, and I'm not going to go into the details of how you do it, it's actually a rather complex, difficult thing to do by hand, but when you diagonalize a matrix, what you do is you actually end up with two separate matrices. So if I take a correlation matrix and I do this procedure called diagonalizing the matrix, it's a procedure that's going to take that correlation matrix and separate it into two parts. And it will produce one matrix that's called a matrix of eigenvalues, which, oh, there's that word again, eigenvalues. So that's actually how those eigenvalues get calculated, is that when you take your correlation matrix and diagonalize it, it actually calculates one matrix of all those eigenvalues that we've been talking about before. And then it will also produce a second matrix. So when you diagonalize a matrix, it's going to produce two separate matrices. One will be your matrix of eigenvalues, and the other will be a matrix of eigenvectors. And to create your factor loadings, you then just plug in this formula where you take the matrix of eigenvectors, which is typically called matrix V, times the square root of your matrix of eigenvalues, which is typically called L. And that will produce a matrix of factor loadings. Now, I'm not going to ask you to memorize the L and the V in this formula for factor loadings. The main thing I want you to know from all this is that to calculate our factor loadings, what we do is we start off with a correlation matrix, and we diagonalize it. So that's the key thing I want you to know, that it involves this process of matrix algebra where we take a correlation matrix and we diagonalize it. And this is going to be important in just a moment here, but note that if you have a correlation matrix, that means you have ones on the diagonal. That is, and if you have a matrix, the diagonal is from the upper left to the lower right. And if you have a correlation matrix, you have ones on the diagonal and correlations on the off diagonals. That's just a reminder that that's true. And in just a moment, that's going to be an important thing. So the key thing to note, again, is when we do principal components analysis, what exactly is that matrix algebra procedure that produces our weights, our component loadings? Well, it's a process where we take a correlation matrix and we diagonalize it. And that will eventually produce, with one additional little calculation, that will produce our factor loadings. Okay, now let's see how this contrasts with doing factor analysis. So now let's look at how we would extract factors if we're doing what is probably the most popular approach to doing factor analysis proper, which is something called principal axis factoring, or it can also be called principal factors analysis. So principal axis factoring, principal factors analysis, two terms for the same thing. They're both an approach to doing factor analysis and probably the most popular approach to doing that. And so to do it, here's how it goes. We're going to start off with a correlation matrix, just as we did with principal components analysis. And we're going to diagonalize that correlation matrix, just as we did with principal components analysis. But we're going to do that with one little tweak. So normally, if you have a correlation matrix, you have ones on the diagonal. You can think of the ones on the diagonal of a correlation matrix as indicating what is the correlation of a variable with itself. Or you can also think of that as what is the total variance of a variable if everything's turned to z-scores prior to analysis. It's the standardized variance of each variable. So normally, a correlation matrix has ones on the diagonal, and we're going to replace those ones with estimates of the communality for each item. And that's it. We simply take the ones off the diagonal, replace those ones with estimates of communality, and then we diagonalize that matrix. And that is the sole difference between principal components analysis and factors analysis, or specifically principal axis factoring. Now, we've talked about the communalities before. Recall what they are. The communality is the sum of the squared factor loadings for an item. And the communality tells you how much variance in an item is explained by all the factors taken together. And by replacing the ones on the diagonal with communalities, it's a way of making an adjustment to account for measurement error. It's a way of saying if there's a 1 on the diagonal, it's as if we're saying the total variance of an item is all true variance. And if we replace that with a communality, we're saying, well, the true variance of this item is a little bit less than 1. So the communality, we're thinking of that as an estimate of what is the portion of the variance for that item that is actually the true variance. And it will be a little bit less than 1, and that's essentially making an adjustment for the fact that that item is not going to have perfect reliability. So the basic idea, we simply replace the ones with communalities. Now, with that being said, we now need to say, well, how do we estimate those communalities? And it turns out there's actually several different ways we could use to estimate communalities. Probably the most popular approach, and the one that SPSS uses, goes like this. First of all, we're going to take each item and create a regression equation where we predict that item using all the other items. And we will calculate the R squared, the percent of variance explained in that item when it is predicted using all the other items. And then we're going to use that R squared as an estimate of the communalities. We will take that R squared and we'll put that on the diagonal. And so we'll do that for each item. We'll take each item on our questionnaire. So if we have a 6-item questionnaire, we will do the 6th time. Take item 1 and use the other 5 items to predict that. take item 2, take the other 5 items to predict that. And so we'll get an R squared for each item, which is the percent of variance explained in that item using all the other items on our questionnaire, or using all the other items on our assessment instrument. And we'll take that as our initial estimate of the communalities. And so we'll put those R squareds on the diagonal. So each item will have its own R squared, and we'll put that on the diagonal for each item. We'll replace that 1 with the communality estimated from regression. And then we're going to complete our factor analysis. We'll diagonalize that matrix and get our results. And then when we get those results, we could then calculate the communalities based on our results, the way I talked about before, where we simply take the sum of the squared factor loadings for each item to calculate the communalities. And the communalities we calculate after doing our analysis will probably not be identical to the ones we estimated when we used regression to try to estimate the communalities. So what we're going to do is then take those new communalities, the ones we just got when we ran our factor analysis, and we're going to run a factor analysis again using those communality estimates we got from our first factor analysis. We're going to take those communality estimates and put those on the diagonal and run our analysis again, and then we'll get new communality estimates. And then we'll keep doing this. Then we'll iterate. We'll keep doing this. We'll get new communality estimates from our factor analysis. We'll put those on the diagonal, run our analysis again. We'll have our correlation matrix, put our communalities on the diagonal. We'll diagonalize the matrix. We'll get new results. And we keep on doing that, replacing our old communality estimates with new communality estimates. And we'll do that over and over again. We'll iterate until we get to the point where we're not changing much, where every time we're getting essentially the same communality estimates. In other words, we're going to iterate until our solution converges, till it's not changing from one analysis to the next. And at the point when the solution converges, we stop and say, okay, this is our final solution. So that is how we would go about doing a principal axis factor analysis. It's, again, the same process as principal components analysis, where we take a correlation matrix and do this thing called diagonalizing it. And the key difference is, with a principal components analysis, you leave the 1s on the diagonal of the correlation matrix. But when you're doing principal axis factoring, you replace those 1s with estimates of communality. And another approach you can use to doing a factor analysis proper is to do something called a minimum residual factor analysis. This is somewhat newer than the other approaches we've been talking about up to this point, and it's not used quite as much, although it might be becoming more and more popular, so it'd be good to be familiar with this approach to doing a factor analysis. So to think about this approach, let's go back and consider how we extract factors. So I've been talking about all along this process where we try to find factor loadings that we can use to create a factor score, such that that factor score will explain as much as possible of the variance in each x variable. So the goal has been to explain as much as possible of the variance in each x variable. Now we're going to shift that goal here for minimum residual analysis to something just slightly different, that rather than trying to explain as much as possible of the variance in each x variable, we want to try to produce a solution that will produce the smallest residuals in our reconstructed correlation matrix. Recall that we talked about 2 different ways that we can look at how well a factor is working. We could look at how much variance in the x variables is explained by the factor. That's one way. But then we also talked about how we can reconstruct the correlation matrix and the extent to which the reconstructed correlation matrix matches the actual correlation matrix also gives us an index of how well that factor is functioning. And if we have factors that explain 100% of the variance in our items, then we will also perfectly reconstruct our correlation matrix. So with minimum residual approaches, instead of trying to produce factors that will explain the maximum amount of variance in the items, we're going to try to produce factors that will reproduce as accurately as possible the reconstructed correlation matrix. So we want to find factor loadings that will produce the smallest possible residuals in the reconstructed correlation matrix. Or to be precise, it's the off-diagonal residuals, that is, the correlations. We want our reconstructed correlations to come as close as possible to the actual correlations. And if we use this procedure, it will actually give us something that's very, very close to what we would get if we were to, say, use a principal axis factoring, but it could be just a little bit different. Just two slightly different ways of figuring out how do we go about extracting factors that work the best in explaining variance. Do we want to try to think of it in terms of we want to explain variance in our x variables, or do we want to think about it we want to minimize the residuals in our reconstructed correlation matrix? Two slightly different ways of getting at the same thing. The minimum residual analysis focuses on a solution that will minimize the residuals in the reconstructed correlation matrix. And then, once you have the results, you can use those results to estimate the communalities. And so we don't have to go through iterations at that point. Once you have your final solution, you can just use that to estimate your communalities. Now, one thing to note about doing a factor analysis proper, and this would be true regardless of whether you're doing a principal axis factors analysis or if you're using the minimum residual approach, either way, if you're doing a factor analysis, then your results are going to be influenced by your communalities. And note that your communalities will increase as you extract more factors. Recall that your communalities indicate how much variance in an item is explained by all the factors. So if you extract one factor, the communality is the amount of variance explained by that one factor. If you extract two factors, it's the amount explained by both factors, and that will be a little bit more than is explained by just one factor. And if you extract a third factor, then your communality will go up. So each time you extract another factor, that's one more thing you're using to explain variance in your items. And so as you extract more and more factors, the communalities increase. So how does this influence the eigenvalues and the percent of variance explained when you're doing factor analysis proper? So regardless of what procedure you're using, when you're doing factors analysis, what's happening is that you're using a system that will only explain the common variance. In other words, it will look at those communalities, and those communalities will be estimates of what is the reliable true variance in that item. And those communalities will be estimates of what the true variance is, and the analysis is going to work so that we'll only explain that true variance, and it will make allowance for whatever's not the communality, that leftover stuff, that will all be measurement error. And so if you have communalities that are low, it will assume that there's a whole lot of measurement error and that there's not a whole lot there to explain. As your communalities increase, it will assume that there's less and less measurement error and there's more to explain. And so if it's only explaining the common variance, that means when your communalities are low, you're going to have smaller values and you're going to have smaller eigenvalues. And if your communalities are high, then you'll have higher loadings and higher eigenvalues. So taken together, what this means is that as you extract more factors, your communalities will go up and your eigenvalues will go up. As you extract fewer factors, your communalities will go down and your eigenvalues will go down. The amount of variance you can explain in each item shrinks as the analysis assumes that your items become less and less reliable. So when you have low communalities, because you haven't extracted very many factors, then the analysis makes the assumption your items aren't very reliable, so there's not a whole lot of variance to explain, so your eigenvalues will be low. The percent of variance you explain will be smaller. And when you extract more factors, then that goes up. Note that this is different from principal components analysis. Recall that with principal components analysis, when I calculated the eigenvalue for my first factor, that didn't change when I extracted my next factor. And those eigenvalues and the loadings didn't change when I extracted another factor. With factor analysis, everything changes. When I extract one factor, I get one solution. When I extract two factors, it will say, oh, your communalities just went up. There's more variance to explain. I can make all these values a little bit bigger. And then if I extract a third factor, it will say, oh, look at that. Your communalities just went up further. There's more reliable variance there to explain. I can make all these values a little bit bigger. So when you're doing factor analysis proper, your eigenvalues will go up and down. They'll get a little bit bigger and a little bit smaller depending on the number of factors you extract. As you extract more factors, your eigenvalues go up, and as you extract fewer factors, the eigenvalues go down. Whereas with principal components analysis, your results were not influenced by your communalities. You didn't get, if you had a high communality or low, it didn't make a difference. And if I extracted more factors, the results from factor 1 stayed the same after I extracted factor 2 or factor 3 or factor 4. Even though the communalities would increase as I extract more factors, the results aren't influenced by the size of those communalities, so they'd stay the same regardless of how many factors I extract. So in sum, the eigenvalues are unchanged for each factor regardless of how many factors are extracted for principal components analysis, but that's not true when you're doing factor analysis proper. So considering all that, let's note some differences that we might find between a principal components analysis and doing a factor analysis proper. So noting that if we do factor analysis, we're making an allowance for measurement error. And there's going to be an estimate of communality and an assumption that we can only explain the common variance and that there's some degree of measurement error that can't be explained. So when we do a factor analysis proper, it means that we're going to have, in general, somewhat, a little bit, slightly smaller eigenvalues. So when we calculate those eigenvalues, after we make that allowance for measurement error, these eigenvalues in a factor analysis will probably be a little bit smaller than the eigenvalues we would have gotten from a principal components analysis. And so if we take our eigenvalues and divide by the number of items to get the proportion of variance explained, we will probably have slightly smaller amounts of variance explained. So we'll have smaller eigenvalues and a smaller proportion of variance explained by each factor. And also our factor loadings will be a little bit smaller. And as I note down here, the difference is usually pretty small. It's usually not a big difference. But that's one way, if you were compared two analyses side by side, and I asked you which one do you think is a principal components analysis and which one is a factor analysis, one clue would be if the eigenvalues were a little smaller, the proportion of variance were a little bit smaller, or the factor loadings were a little bit smaller, then the best guess is it was probably a factor analysis. And if those eigenvalues were larger and larger factor loadings, it might be a principal components analysis. So that's one thing to note about one consequence of choosing whether to do a principal components analysis or a factor analysis. So to clarify what I was just talking about, here are results from a parallel analysis. And these results show a scree plot, one scree plot using a principal components analysis with the x's. Whoop, my marker's doing crazy things there. And another scree plot for doing a factor analysis. And you can see the scree plot for the principal components analysis has eigenvalues that are all just a little bit higher than the eigenvalues I get if I do my factor analysis. So the eigenvalues for the principal components analysis are all just a little bit higher than the ones for the factor analysis. And also, if I get the parallel analysis, the estimated eigenvalues that we get just based on randomness alone, the top red line here, that's from doing a principal components analysis, and the bottom one is from a factors analysis. And so even there, our eigenvalues from the principal components analysis are higher than the ones for the factor analysis. So the main thing to note there, again, is that the eigenvalues tend to be a little bit higher when we're doing principal components analysis and tend to be a little bit lower when we're doing factor analysis proper. Now, let's assume you've done all the things we've talked about and you've done a factor analysis or you've done a principal components analysis. You went through the steps of deciding how many factors to extract, and you extracted your factors and you rotated them and you have your final results. You have your table of factor loadings if you've done a factor analysis, or you have your table of component loadings if you've done a principal components analysis, and you have your results and you are ready to interpret them and decide what they mean. How do you go about deciding what your results mean and how to interpret them? I've mentioned before that one of the key things to look for is we want to find a simple solution. That is, we want to find a solution that shows that each item has a really high loading on one factor and only one factor, and has low loadings on all the other factors. But what do I mean by high loading? And what do I mean by low? How do we decide whether a loading is high or low? And the truth is, well, it's arbitrary. There are no firm guidelines about what is high and what is low, and different people can have different subjective opinions about what should be called a high loading and what should be called a low loading, which makes it kind of difficult for us if it's all subjective. But here is a guideline you can follow, and we can use this for this class. I'm pulling from an article by Comrie and Lee, who suggested some arbitrary cutoffs. Now, these are just arbitrary, but it's helpful. Someone's printed some arbitrary cutoffs, so that gives us something we can use. And so according to their cutoffs, we can say if a factor loading is 0.55 or greater, we can call that a good loading. If it's 0.45 or greater, we can call that a fair loading. And if it's 0.3 or greater, maybe call that a poor loading. And if it's less than 0.3, we'll just say that's so bad it's not even an indicator. That item is not an indicator of a factor. So if we follow these guidelines, what we're looking for is each item to load 0.55 or greater on one and only one factor, and to load less than 0.3 on all the other factors. So again, that would be, if we're going to try to find some kind of arbitrary guideline to follow, this would be the best one I would suggest, is drawing from the Comrie and Lee article. We'll say we want to have each item will have a loading of at least 0.55 or greater on one and only one factor, and that item will load less than 0.3 on all the other factors. And if that's true for all the items on an instrument, if that's true for all the items on an assessment instrument or all the items on a questionnaire, then we could say we have a good, clean, simple solution. The results look really neat and easy to interpret. All the items loading greater than 0.55 on a factor are the items that are indicators of the factor. All the items that load less than 0.3 are not indicators of the factor. Each item is an indicator of one and only one factor, and that gives us nice, neat, clean, easy to interpret results. That is the ideal for what we're looking for. So let's put everything together and look at an example. This is from that data set we were looking at just a little while ago, where we had my ratings on a questionnaire for hard and soft emotion. People rating the experience they had in a conflict with a romantic partner and rating the emotions of how they felt angry, irritated, annoyed, hurt, concerned, and sad, with the idea that angry, irritated, and annoyed should be measures of hard emotion. Hurt, concerned, and sad should be a different factor. It should be measuring something called soft emotion. So this is if I use SPSS, and using SPSS to do, first we'll do a principal component analysis. And let's see what we have here. So we have a table up here showing communalities, and it's showing is for angry, irritated, annoyed, hurt, concerned, and sad. We have 6 items. And this column where it says initial, this is saying what is the initial communality when I do that initial process where I extract all the possible factors, or in this case, all the possible components. So if I have 6 items, we're going to extract 6 components and calculate the communalities. Now, as we recall, if you do that, your communalities will all be 100%. It'll be 1 for every item, and that's what we have here. We just have 1s for every single item, saying, well, we extracted as many components as we have items, and we have a communality of 1 for every item, as we might expect. And so that initial solution where we extract all the possible factors, we also have down here where it says initial eigenvalues. These are the eigenvalues if I extract all the possible factors or all the possible components. So here we have, if we extract one component, our eigenvalue was 3.55. I extract the second component, the eigenvalue is 1.065. The third, my eigenvalue is 0.537. The fourth, my eigen's dropping down to 0.4, and so forth. So I have the eigenvalues here if I extract all 6 of the possible components that I extract. And then it's calculated the percent of variance explained, that eigenvalue divided by number of items. So if we take our eigenvalue, in this case we have 6 items, so the eigenvalue divided by 6 gives us the percent of variance explained by that component. And so we see that that first component explained 59% of the variance. The second one explained 17%. The third explained 8%. The fourth explained 6%, and so forth. And note, as we've talked about before, your eigenvalues decrease with each successive factor, and likewise the percent of variance explained decreases with each successive factor. And then we also have this column over here, the cumulative percent, saying how much variance have we explained altogether by all the factors up to this point. So when we extracted that first factor, we explained 59% of the variance. And then when we extracted that second factor, or I should be saying component, we extracted that second component, we explained 17% of the variance, or about 18% with rounding here. And that means our total cumulative percent that we've now explained 76% of the variance together, or with rounding, I guess that would be 77% altogether with both factors 1 and factors 2 together. And then when we extract that third component, we explain an additional about 9% of the variance, which brings us up to almost 86% of the variance altogether. And when we extract that fourth factor, we extract an additional almost 7%, which brings us up to almost 93% altogether. All these involve rounding that needs to go up. So the cumulative column tells us how much variance we've explained up to that point with all the components that have been extracted up to that point. And then for our initial solution, we also have our scree plot over here, and that's just plotting these eigenvalues right here for these 6 components. So here we have 6 components, 1, 2, 3, 4, 5, 6, and we have 6 eigenvalues. So the first component had an eigenvalue of 3.55. So right here, 3.55, that's our first dot on that scree plot. The second component had an eigenvalue of 1.065. So I'll put that right here, 1.065. The next component had an eigenvalue of 0.537, and so that's 0.537. So the scree plot is just plotting these eigenvalues from our initial solution where we extract all the possible components. Now, in doing this analysis, recall I had my hypothesis, my theory was we should have 2 factors, one for hard emotion and one for soft emotion. This doesn't really produce a really clear scree plot here. It's not really clear, does our big drop occur after this first factor or the second one? If I do that rule of put the pencil across things, kind of depends on how fat my pencil is, but maybe my pencil might just cover up those bottom ones. So maybe we might get 2 factors here. If we use that rule, how many factors have eigenvalues greater than 1? It comes pretty close. But the second factor does have an eigenvalue greater than 1. And so taking all that together, I decided to go for a 2-factor solution. A lot of it was because that was theoretically what I expected, but I did have 2 factors with eigenvalues greater than 1, and I can interpret the scree plot in a way that would say it looks like I've got 2 factors, depending on how I look at it. So I'm going to extract 2 factors. So my initial solution extracted all the possible factors, or all the possible components, if I want to use precise language. And then my extraction solution, that's where I told the computer, now I just want you to extract 2 components. And so now we have the communalities based on just 2 components. So the communality is how much variance in the angry item is explained by just those 2 components, and how much variance in the irritated item is explained by just 2 components, and so forth. So these extraction communalities are the amount of variance explained in each item by just the 2 components that I extracted. And then over here I have the extraction sums of squares and loadings. So where it says total here, this would be the eigenvalue or the extraction sums of squares for component 1 and for component 2, and then there's nothing below that because I only extracted 2 components. Now, because I'm doing a principal components analysis, the eigenvalues don't change when I extract more or less factors. So over here we see our eigenvalue is 3.55. It's still 3.55. We explained 59% of the variance. The first component still explained 59% of the variance. The second eigenvalue was 1.065, explaining 17% of the variance. So that's still the same. Altogether, we can look at these two components and note that altogether these two components together explained 76.9, almost 77% of the variance was explained by these two components. And then I rotated the solution, and actually in the next slide I'll show you rotation based on both orthogonal rotation and oblique rotation. I have over here rotation sums of squares, so this is the sums of squares that we get after rotation. And looking at this, I can tell that this output right here is based on orthogonal rotation, and I can tell that because my cumulative amount of variance explained is the same before rotation and after rotation. Recall that if I use oblique rotation, that's going to make this, I can't really interpret that, and it won't be the same. So because that's the same either way, I can tell this output right here where it says rotation sums of squares loading, that must be based on an orthogonal rotation because the total amount explained did not change. However, what did change was how that variance explained is distributed over my factors. So before rotation, the first factor explained quite a bit of variance, 59.24% of the variance, and the second factor explained much less, 17.78. Now after rotation, I get a much more even distribution where that first factor explains about 40% and the second factor explains about 36%. So after rotation, the percent of variance explained by each factor is more evenly distributed, whereas before rotation, the first component explained quite a bit more variance than my second component. Okay, let's look at what the rotated and actually let's look at the unrotated and rotated component loadings for this analysis. So normally when I do a factor analysis or a principal components analysis, I would decide, do I want to do orthogonal rotation or oblique rotation? And when I report results, I would just report results for one or the other. But for demonstration purposes, here I have all the possibilities laid out on the same slide together. So, there we go. Up in the upper left, we have, this is the unrotated component matrix. These are the component loadings, unrotated. And then here we have the rotated where I used the Varimax. That's the orthogonal rotation. And then down at the bottom, I have the pattern matrix and the structure matrix from doing an oblique rotation. And actually, these are the same loading matrices that I showed you before when I was talking about rotation. So this is the same example. And we saw that with the unrotated solution, it was a little hard to interpret. We had every item loaded high on that first factor, and then the second factor seemed to be kind of a distinguishing between the hard and soft emotion, but we couldn't label our factors easily, and we certainly don't have what I'm looking for, that type of simple solution where each item has a high loading on one factor and a low loading on all the others. The Varimax rotation, if we follow those rules, we see that all of these items do load greater than 0.55 on that factor. And this loading point, we've got a couple loadings that are a little bit high. If we try to use that, if we say they should be less than 0.3, these loadings are a little bit higher than that. These loadings are all nice and low, and these loadings are all nice and high. So we come kind of close to a simple solution there. We've got a few items right here. This hurt item should load primarily on component 2, but it has a little bit of, we'd like that loading to be a little bit lower on component 1, and we'd like that maybe to be just a smidgen lower as well. But part of the issue here, we're doing orthogonal rotation, so we're imposing the requirement that our factors have to be orthogonal, have to be uncorrelated, and we might get a little bit better result if we relax that, and it's certainly reasonable to do so, and assume that, well, our factors could correlate, and let's see what happens if we do that oblique rotation. Which, by the way, it's reasonable to do orthogonal or oblique rotation. I don't have any rules about you should always do orthogonal or always do oblique. And it's somewhat of a matter of preference. Well, I don't know. Do you want to do orthogonal or oblique? Maybe you have a theoretical reason for doing that. In general, though, I probably more often than not use oblique rotation because it seems like in general, it's always reasonable to assume that you're going to have correlations between your factors. And it always is a little bit excessive to try to assume that your factors should be orthogonal. Although there might be some times where I'm trying to choose items and I want them to be as distinct as possible, and I might use an orthogonal rotation because my goal is trying to find specific items that will produce that type of structure, and I'm particularly looking at that, and so I'm using orthogonal rotation. But for the most part, I probably gravitate towards doing oblique solutions. And so here is the pattern matrix, and recall that's the one we usually interpret when doing an oblique analysis. So this is the using the Oblubin method, and so here are our factor loadings for. We have angry, irritated, annoyed, produce really nice high loadings on factor 1, and these are all sufficiently low our soft emotion items have sufficiently low items on factor 1 or component 1. And the soft emotion items all have high loadings on component 2 and all have really low loadings on component, or the hard emotion items all have very low loadings on component 2. So when we look at this pattern matrix from our oblique rotation, we get really nice results. These definitely conform to a simple structure where each item has a really high loading on one and only one factor, and each item has low loadings on all the other factors. Every item has a loading greater than 0.55 on one factor and loads less than 0.3 on all the others. So that's really neat. Over here we have the structure matrix. That's not as often interpreted or looked at, but this is looking at the actual correlations between the factors and the items. And we see that there actually is some degree of overlap, and this is what we saw before, is that the hard emotion items actually still do have some correlation with that second component, and our soft emotion items still do have some degree of correlation with that first component. But again, usually the pattern matrix is the one I would interpret. And if I was publishing these results, I would probably focus on the oblique rotation and report the pattern matrix. And that's probably the most common way to report this type of analysis. And in that case, our results here look really nice and clean. In fact, it's probably unusual to do an exploratory factor analysis and get results that look this clean. This is really actually very clean results. So now let's look at the same exact example, but let's do a principal axis factoring. We'll do an actual factor analysis. So here is the SPSS output from a principal axis factoring analysis of our data set. So we have the same 6 items here. Note that we have the initial communalities, and when we were doing a principal components analysis, the initial communalities were all 1 for every single item. But now with the principal axis factoring, when we extract as many factors as we have items, we don't explain 100% of the variance, and our communalities are not 1. So these are estimates of the communality is the estimate of the common variance that the item has with all the other items, and we're assuming that the remainder is measurement error. So the communality for the angry item is 0.67. The initial communality for the irritated item is 0.584, and so forth. And then down over here, we have our initial eigenvalues from that solution where we extracted all 6 factors. We have 6 items. The maximum number of factors we can extract is 6, so we extract all 6. And so here are the initial eigenvalues that we get. Now, for some reason, when SPSS calculates these initial eigenvalues in the scree plot, it's actually going to resort back to our principal components analysis. And so you note that actually this section right here is going to be identical to what we have here. And I'm actually not sure why SPSS does that, but whenever they give you the eigenvalues for the initial solution, even though we've told it we're running a principal axis example, it's going to give us the eigenvalues for the principal components analysis. But it's illustrative here because now that we have that, we can compare it to what we get at other points in our analysis. So, and maybe that's why they do it, I don't know. So anyway, so here we have the extraction sums of squares loading. So so I've done the same thing. I've decided to extract two factors. And when I extract two factors, here I have the extraction communalities. So the communality for the angry item is 0.86 when I extract two factors. When I extract two factors, it's 0.64 for irritated, 0.5 for annoyed, 0.73 for hurt, and so forth. And actually, this concern item has it's a little bit on the low side. It's not sharing as much variance with the other items as the others. So here are the extraction sums of squares. So my first factor had an eigenvalue of 3.255. It explained 54% of the variance. And my second factor had an eigenvalue of 0.749. It explained 12.48% of the variance. And note that these no longer match. And it wouldn't have matched even if I did the initial eigenvalues based on a principal axis factoring. It still would not have matched. So, and the issue is that depending on how many factors I extract, the communalities will be different, and it's only going to factor the common portion of my items. And so if the common portion changes depending on how many factors I extract, then the solution is going to change depending on how many factors I extract. So we see the eigenvalue for my first factor, 3.25, it explained 54% of the variance. The second factor explained about 12% of the variance. So altogether, we're explaining about 66% of the variance. Now, if I back up here to a previous note here, that with the principal components analysis, so when we did that, we saw that we explained altogether our cumulative percent with two components. We explained almost 77% of the variance. And now we're doing principal axis factoring, and we're only explaining 66. It's not a huge drop, but we're explaining a little bit less variance. And that follows the same procedure I talked about, or the same principle I talked about before, that when we do principal axis factoring, or a type of factor analysis, our eigenvalues and our percent of variance explained are going to be a little bit less than if we do a principal components analysis. And then over here, I have the rotated sums of squares. And we can see again, I must have done this based on a orthogonal rotation, because the cumulative, the total percent of variance explained over here for rotated is the same as the unrotated solution. The key difference is that with the unrotated solution, let's go over here, our two factors explain fairly different amounts of variance. The first factor explains a lot of variance, 54%. The second factor explains notably less, only about 12%, whereas after rotation, I've got 34% and 32%. It's more evenly distributed between my two factors. The percent of variance explained by each factor is more evenly distributed after rotation, whereas there's a greater discrepancy with the first factor explaining most and the second factor explaining notably less before rotation. And then finally, here are the factor loadings from doing that factor analysis. And again, I would not report all these different approaches in a single paper if I was publishing this, but for illustration purposes, we have the unrotated solution, the rotated solution using the Varimax, the orthogonal rotation, and the pattern matrix and the structure matrix from an oblique rotation. And these are essentially the same results we saw before. If you look at them, you'll notice it's pretty much the same patterns we saw before. For example, if you look at this pattern matrix, we see that angry, irritated, and annoyed all have fairly strong loadings on factor 1 and have weak loadings, and the soft emotion items have weak loadings on that factor. And the soft emotion items all have strong loadings on factor 2. And the hard emotion items all have weak loadings on factor 2. So we have that same nice, clean a simple solution where each item has a high loading on one and only one factor and a low loading on all the other factors. Although if we compare, we note that these loadings are not quite as high as we got when we did a principal components analysis. So for example, we got a 0.66 and here's a 0.625. So those are still good loadings. If we use that 0.55 cutoff, they're still definitely higher than that, but they're not quite as high as we saw when we did that principal components analysis. And again, that follows that same principle that I talked about, that when we do factor analysis, our factor loadings are likely to be a little bit smaller than if we do a principal components analysis. So that is everything I have on exploratory factor analysis.